Hey everybody, this is Brad Dyke. How you doing? I am out here and about doing all these builds and stuff using my transition from my old 720s to my 730s, and I'm contemplating some natures about I/O disk space versus ratio, bandwidths versus IOPS, and so on. Now, if anybody knows what IOPS means, that basically means your I/O versus your times your storage capacity, which gives you a total sum of IOPS. And in the old days, when we worked on storage arrays, we had these physical hard drives that were blocky and heavy, and they spun at 10,000 or 15,000 or 1,700 RPM, and they had what we called a defined path for data. And that was for many years in the days of Data General and SCSI and then Fiber Channel and then SAS and Advanced SATA and so on, that the inherited bandwidth problems, the bottlenecks as we used to call them, came from the drives. So these guys only added a little bit of I/O to the equation to the overall IOPS capacity of your environment. In the days where we used to use RAID controllers, kind of stemmed it a little bit because they had a little bit of memory on them and they can buffer some of it, cache that data, and then later write it back to the drive as the drive can handle it. But that didn't work very well. Why? Well, because when you look at storage arrays, and they get bigger and bigger over time, and petabytes are out there, and so on and so on, the reality of the fact is that the math isn't adding up. Controller cards can only perform so well before they also become part of what we call the downscale effect. So what that basically means is the amount of disks that you have up going up versus the amount that your controller can support going down, that X mark is your optimal capacity. And that's how you design your storage environments in blocks of 25 to 64 to 96 drives and so on and so on. And in this sequence, of course, by a divided factor of 3, because usually you have 3 channels per bus. So with that being said, it was getting pretty messy. EMC was trying to answer that with more sophisticated controllers, much larger controllers, but the reality of the fact is Data General had it right. They chose to use systems or computers, motherboards, basically. It's what they were, by the way. 2 separate motherboards, one on top of the other, and we used to call these guys redundant work states. In other words, they were redundancy in their functionality. They each had exactly the same as the other, and they were motherboards with memory and capacity and handling on board far greater than a controller. So with that being said, the key detail here is the reality of the fact that, okay, now we've just changed the world. Controllers can outperform even better than they used to in the days of I/O cards, i.e. like a RAID card. You had a controller, usually 2 of them, which is the preferred path. And these controllers, 2, 4, 6, 8, 10, would put tremendous amounts of memory in front of these spinning disks. And they eventually became known as entities such as, for instance, a Clarion that used Navisphere technology, or a dual redundant head for a Shark, an IBM Shark platform. The key thing is these were computers, and believe it or not, EMC's secret sauce was Windows NT40 workstation. That's right. I remember that. We used to connect up a video card up to the, a video port to the output on the back, and you would see NT operating system 4.0. We were far beyond that, but they were using that because it was the most inherent and stable platform they could use at the time. So, hence we jump ahead of the game, and finally we get introduction to these little guys. Now, if you notice here, this, hang on a second. So, this is a 2.5 inch drive, 10,000 RPM, 500 gig capacity. Very fast, but kind of slow. Why? Because it's a spinning disk array, which means the physical motions restrict the functions of its I/O bandwidth because of its design. Now this is an SSD drive. Notice it's also a 2.5 inch drive configuration, but this is to placate the standard. This is not an SSD drive. This is a plastic shell. That's all it is. This is the SSD drive. Much smaller, much more functional, no moving parts. And if you look, let's see here, right there, it's SATA. Just like, very much like a SAS. So, it will work on SAS, it will work on SATA, it outperforms both because the IOPS of this guy is staggering. And then all of a sudden, now we have a new dilemma. With SSDs coming into the scene, the industry knew this. And they said, oh, let's slow things down a little bit because we have to learn how to transform these into a profit. And I got that. And that makes good sense because they are in the business of making money. So SSDs were not readily available for anything more than a cache drive. And a cache drive is kind of a weird drive. It is purposefully restricted. It's kind of small, 100, 200 gigs. It's properly built. I'll give it credit. It has an aluminum housing around the actual logic chips. Great heatsink. It will last for decades because it will never get hot. Unlike this little guy, which has no heat sinks on it at all. And it'll burn out in about 4 years if you use it consistently. Probably last a little longer if you intermittently use it like I do. But it came out of the shell of this guy, which is pretty cool, right? And because it can fit so elegantly in a footprint, if you take an enterprise caddy housing like this, if you take a look at this guy, it's a very interesting little piece of hardware. It's got a daughter bus interface card. All of them do, some type of interface card here. And it is a logic board. If you look at it, you'll see it inside there. And it's designed to basically controllerize the nature of the hookup that what you're going to do. So I'm taking this little tiny little rinky-dinky thing here, and I'm going to put this guy right in here. Ta-da! That's it. Nope, it won't break, it won't fall off, it won't come out. It's in there good, and it's in there solid. You can do this over and over and over and over. Now, the only thing that I would recommend that you do is, during that process, is you put a heatsink in there a little bit. The adhesive heatsinks for like Raspberry Pi, that does help the memory a little bit. It's not super great, but if you're going to get intensive, not a bad step to take. But as you can see, this is a heck of a lot better than this. Much heavier. You have to keep it in place and everything like that. But the other important detail that you've got to remember here is a really cool little detail. This is a little secret, I'll tell you now. Sometimes we would do this with our hard drive analysis engines running, monitoring the hard drives. And you would go up to like a whole rack of hard disk and you would scream at it really loud or introduce a high-pitched sound, a loud high-pitched sound. You would see the performance of the disks drop because these guys are sensitive to sound waves. That's true. So you think in a data center, it's pretty noisy, right? So they started realizing that they needed to move the fan systems out. They needed to get the airflow noise down better, maybe better contain it. And that way the performance would maintain at a fairly decent level for the spinning disks. When in reality, what we really needed to do was to go to something that had no relevancy to sound waves. And that's basically, modernized microelectronics. So with that being said, today's technology that we have at this time is indicative to the hardware always being ahead of the game of software. It's true. Let me ask you a question. Can you run software without hardware? No. Can you run hardware without software? Yes. So when software is put on top of hardware, it becomes beneficial. And when it becomes beneficial, it acts as a multiplier by providing you more serviceability and functionality by the add-in of the software. The problem with the industry has always been that the hardware, has been way ahead of all the software that needs to be truly written to take full advantage of the hardware. So that unfortunately terribly means that 75% of all the hardware we've ever produced never had potential. And we have spent trillions of dollars already. Finally, in the past 6 or 7 years, people are writing software that's starting to catch up with the hardware. And the hardware is plateauing in Moore's law and all of the variables in the equation. But the hardware is platforming, and it's going to start getting fewer and fewer in between in benefits and added values. It's where the software can maximize the effect of the hardware itself. And then at that point in stage, technology will eventually reset itself for the next level of technology. This is the same effect we saw with mainframe technology, the same effect we saw with the x86 design implementation. And then, of course, we'll have something, probably a pseudo-hybrid between quantum and non-quantum state technologies. Very important details to understand. Our software coders, I work with software coders, and I maintain and do the operations DevOps side of things so that they can continue to introduce more and more and more functionality to the stuff they're putting it on, like this hardware to start with. So with that being said, this discussion was to talk about the nature of bottlenecks. Strangely enough, at the very beginning, hard drives were the bottleneck of the industry, and as it progressed down the road, the controllers became the bottleneck because the hard drives like SSD or NVMe can greatly outperform most controllers that we have in the industry because they're just not able to be faster than the drives, which means we will be going to what is known as open busing. And open busing basically means to create new sets of travel path lanes that match the travel path lanes of the disk drive's capacities and its ability to handle I/O. That's kind of like the difference between an x86 Intel processor that has all of its ingrained circuitry software written to the chip versus a graphical processor which has nothing in it and you have to fill it up and then empty it and fill it up and empty it. Both have values, and you have to use both designs in the incorporation of working with ultra high bandwidth NVMe kind of like storage capacities. Even then, because of the same principal rules that affect our computer systems, affects the storage disks, because eventually you can only get so small and you have to deal with so much heat and you have to deal with so much interlatency effect between integrated circuits and so on, that you'll eventually plateau the high performance capacity of this. The only thing that can work better than this is something that is not made of atoms. That's right. It would have to be made out of electrons, neutrons, and protons, which is a different theorem altogether. Now, what that basically means is if you know how to integer electrons and protons in chains, you can formulate data strips. In other words, you can form something like an old magnetic tape of sorts, but you're doing it through a string of electrons and protons and neutrons in the air. Now, it's already been proven by lightning, specifically kinds of lightning like St. Elmo's fire, which is ball lightning, that it is very unique to see that electrons can hold property attributes independently in an atmospheric environment and stay there and not lose its cohesion. It would lose its intensity, it would lose its voltage, but it's still there. It's just much, much, much less because it doesn't need all that energy to maintain its cohesion of sequencing electrons, neutrons, and protons. Now, this goes below the threshold of quantum technology, where quantum computers are basically working at the atom level and using a series of quantum fluorine atoms, or equivalency of, in succession and order, to anode and diode a question for an answer at the end of that string. Now, because you can do 0, 1, and 0, 1, you have a trinary state, or it's basically trinary code opposed to binary code. Now, I'm pretty sure we won't be able to do the intricate integrations that I can see in my head in such a way so that we could properly tag electrons and photons and protons in the proper sequences in a way without the need of something similar to like a quantum platform that could correctly sequencing out those values in order to efficiently be able to tag electrons, neutrons, and protons together. The other key thing is containment. How do you contain it? Well, that's the beauty of it. You don't. It's a frequency. Because it's a frequency, it's out there constantly. It just resides in the environment. And you're saying, well, I don't understand. How do you do that? Well, you don't need to have to understand it. You just have to understand how it happens in nature. When lightning comes down, you can actually bring out a couple of devices days later, look at the space where the lightning struck, and you can see the lightning is still there. That's because when the lightning strikes, when a pattern comes down, it strikes an initiate, and the initiate stays there, but it devalues, or in this case, de-energizes from its high-powered state into an extremely minor state. But it's still there. We can see it. So we don't have to go off and prove that fact. We just know the nature of how that happens. So, in other words, if you're able to, you could create an anode-style lightning strike process that would properly sequencing out the electrons, because that's what you're doing here. You're trying to get the electrons to represent a stack of code in a trinary or binary state. And at that point stage, it can contain that information in the width of an electron. So that means, in a nutshell, that in the span of a couple of inches, that might be 6 or 7 inches long, you could store quadruple amount of capacities to that of not a gigaflop, but not a petabyte, zettabyte or something like that. It's much bigger than a petabyte of capacity, and a very small amount of space, because one line, and that's it. You could even prelong a execution control file at the top that can descript it correctly, and at the end give you a conclusion. Basically storytelling. Now, the key thing about this is when you create it, you can't rewrite it. So how this process happens has to be done in a certain way so that it's accurate 100% before it's written. That's the Achilles heel, because whatever you write is there. So you have to make sure that you're doing the process correctly. So in the days of electronics, of spinning disks and mechanical devices versus non-mechanical devices versus a spark of lightning that can contain binary strikes in that equation, these are all basically still the same. You have a medium. What is the medium? Well, in the old days of rear-to-rear, it was tape, magnetic tape. And in the world of hard drives, it was a platter, a magnetic cohesive platter. And an SSD and NVMe, circuitry chips that have attributes that go 0 or 1. Same kind of principle as magnetic platter. And in the space of air, not just air, that's the key detail, an atmospheric environment that's heavily sustained by a lot of static electricity environments. Those are important details because they maintain the integrity of the electron form. They can provide that little strip of magnetic tape, if you want to call it, for that process. Now, the only thing that's going to be more effective than that is, I'm going to say it now, you may have heard of this in the past, the cup of coffee that can store all of the world's data. That is correct. If you had a medium that you put into a cup of coffee, and you can correctly carouse that environment by atomic structure only, the amount of data that you can hold in that cup would be the world. And that is impressive. But the process to read it, the process to write it, and the process to sustain it is extraordinarily complicated. And so fluid mediums are not always the best in the world because they're fluid, unless they're contained. What do I mean by that? Well, a cup, or an ocean, or a lake. The key thing is, if you can maintain the integrity of the liquid, you could write data in that liquid and keep it there until you need it to come out. It's the next level of capacity storage that exists out there for us. Something to think about. Theoretically, it's viable. Getting to that point, not so easy, because we still need to facilitate the understanding of using atoms, and you got to understand how fantastic that is. You're talking to an atom. You're asking an atom a question, and it's going to answer you back. Now, I'm not going to say anything about sentience or anything like that. No. I'm saying if you know how to ask the question, it can answer back. And that does preclude that there's something more to the matter that exists in our world. And all of this is being generally derived from the nature of how we use storage hard drives. So I took you a little farther out there in the world of theorem about storage and capacity, but I come from a world of storage and operations and stuff, and we're always constantly trying to figure out better ways to store things, newer ways, ways that are not so, demanding. So with that being said, this is my conceptual video for this go around, and I have another video which I was talking about for Proxmox buildouts for working with node configurations, and I'm going to be working on a couple more formats that'll be coming up soon for you, and some of it will be conceptual, some will be hardware, and so on. This is Brad Dyke signing off. Bye-bye.